Hello, my name is Anton Antonov. I'm a senior research scientist. My presentation is titled Simplified Machine Learning Workflows Overview. This presentation is titled Simplified Machine Learning Workflows Overview. My name is Anton Antonov, and I brand myself as a senior research scientist. I worked for Wolfram Research 7-8 years, and then moved to do some other things. So I would like to manage the expectations for this presentation. So this is an advertising presentation. It's not technical. If you think that you'll learn the simplified machine learning workflows here today, maybe you can do today, but not in this presentation. So I'm going to very quickly say what is this about, and then we are going to do into some more dedicated explanations. I do have several general discussion topics. We'll see what is the interest and how much time we have. You can see there are like 55 slides. I'm not going to go through all of the slides, pay equal attention to all of the slides. All right, so this project I have, there are several goals. I want to speed up the coming of the next artificial intelligence winter. I want to replace expertise with enthusiasm. And you know what Stephen said yesterday in his opening speech, I would like to make the future more evenly distributed. The future is already here. It's just some people don't experience it, like say people like me, in the same way. So I want to facilitate the professional life of code baristas. This is people who just go to different places and serve code for whatever kind of professional requirements they have. You are going to see a manifestation of the principle cloths that have no emperor. It's the other way around. Not emperor with no cloths. It's cloths without an emperor. I'm using this to do whatever I'm going to be showing. All right. So what are the main machine learning workflows? So there's like this 80-20 rule or Pareto principle. I would say between 60 to 85% of all machine learning workflows in this, I would say 4 or 5 type of subcultures: classification, regression, latent semantic analysis, recommendations. I'm biased about recommendations, but I think they should be included, and data wrangling. Data wrangling is not machine learning per se, but some people successfully convinced me to include it. So yeah, it's included into this. Event records transformations, what you see here, this is some sort of data wrangling. So as first examples, let us see this commands where the short, abstract enough, non-specific, but you can see I'm going to recite: make a classifier over DS Titanic. Use the document collection A abstracts, extract 32 topics, do quantile regression. So you can see here, this code has been generated using this magic function concretize. And I'm going to explain what is this. So this here, what you see are monadic workflows. This is the simplified. These are the simplified machine learning workflows. They're represented in this pipeline of transformations. Another part of the simplification is how we transfer, convert natural language text into executable code. So the simplifications is done in this project, is done in 2 ways. One is that I have abstracted the common parts of all these subcultures, like workflows, right? And there are flow charts, and there is also monadic packages for each of the workflows. The code generation, I would say this is a simplification part, because the code generation is not just to Wolfram language, it's targeting other languages, like say Python, R, sometimes Julia, sometimes Swift, sometimes Raku. And I claim that this simplification is both operational and theoretic because of the monadic workflows. When you hear things like there's nothing more useful than a good abstract theory, it's about that, right? If you don't know what monads are, you might have some idea after this presentation. So there's a variety of interfaces to bring this to the end user, this monads or whatever this And you can see I have done some, there's some dashboards with the web service. There's like a chatbot work for Discord and Slack. There's a resource function in Wolfram Language, some Packlets I'm planning to do as a command line interface, Siri shortcuts, and so forth, right? So this shouldn't be underestimated, right? Like this kind of interface work is important. Actually, let me see. This is the dashboard while it is loading. Let me see. Do I have? You can see I have some kind of interface here which generates certain code. You can see here how I generate programming code. Like say, let's use Wolfram Language since we have this. How will you see this? Yeah, I can. Of course, I can if I can translate to a programming language, I can translate English also to other natural languages. Actually, since some of the people I worked with, for some reason, speak Spanish, maybe this is more. There's a more people in the audience who can read this. All right, so so there's a this is an important part of the simplification. Another part which I'm saying here, right? Command line interface. This is an illustration. This is a shell command, right? So I can use this. So this actually generated something, right? Alternatively, I can use a shell command, right, to go to this web service. And you can see here I'm getting some JSON which says what was happening, what exactly is the command, what is the code being returned, right? All right. So that's very important. I can convert the notebooks into certain domain-specific language mode. And here I can make this execution, right? This generates code. If I run this, this is going to produce some stuff, right? So similarly, this somebody was talking about Julia, how much better is Ricardo, how much better is interfaced in Wolfram Language. So I put this here, Julia code. So you can see here, this DSL cell knows that it's about data wrangling, knows what it needs to generate Julia code, and then it uses this natural language text to generate Julia code. If I do something like say, I don't know, like say we do Python and then pandas, this should produce Python code, right? Okay, this is again part of the simplification, part of the, making the whole thing easy and so forth, right? So the way we do this is there's a certain abstract domain, right? So we start working with, we get interested in it, curious, whatever, scratch our heads, right? And we make two things. One is monadic package, like say, this here, what you saw is a monadic pipelining, right? This is a latent semantic analysis, monadic pipeline. And I also make something very similar, but with natural language. I develop certain grammars which correspond to this, to these commands. And so at some point, we want to marry the two, right? We want to make a single line interpreter. This is what you saw here. This here is a single line interpreter. Each of these lines is interpreted separately, and the code is produced. And then we can even go further and make some full-blown conversational agents, chatbots, whatever, right? Rigorous testing is required for this. It's extremely important. This kind of systems were assumed to fail. Where basically failure is the normal mode, right? People misspell, people don't know what they're doing, and so forth, right? All right. So what I'm showing here is we've done through something called natural language processing template engine. So there are two approaches to do what I was showing, from converting from natural language. We can use neural networks, we can use context-free grammars. So I showed both at this point. My presentation on Friday at 10 a.m. is going to expand more on this natural language template engine, how it is done. For the natural language template engine, I'm using Wolfram technologies, find textual answer, I'm using neural networks. For the context-free grammars, initially I was using Wolfram Language, then I switched to Raku. All right. So this is just I'm showing how this is the context-free grammars translations are being used. One convenient thing to do is that when you execute these commands, the code which is generated is being put into the clipboard. Mathematica has a function copy to clipboard, and you can just need to do some kind of semicolon here, and we generate this code, right? Obviously, I mean, as I mentioned earlier, if I can translate this to a programming language, I should be able to translate this into other languages. So here, this is a multi-language system in both senses. You can enter commands into it with Bulgarian or English. At this point, I would like to introduce more languages. So this is also a marketing talk. If somebody wants to collaborate and introduce, include more languages into this, I'll be interested to talk to them. If for some reason you don't know Bulgarian, you can see here I've translated these commands here from Bulgarian to English. So okay, and what is kind of happening, and especially when we saw it here, right? So what you see here is it's a similar type of diagram. So I'm using any kind of speech recognition, audio to text program. I can interface this into different. I can interact with it from Mathematica notebooks, Jupyter, Markdown, whatever, right? And then I go to a certain web service which uses this language and a constellation of packages in that language called CRO. That service also connects via 0MQ. 0MQ is used a lot by Mathematica, by Wolfram Language to connect to Python, Julia, and so forth, right? R and so forth. And I'm connecting to Wolfram Engine in order to use the function concretize, which is provided by the NLP template engine. All right, so obviously this is not just for machine learning. It can be also, right? Let me see. Can I make a live demo here? Right. So let's see. We do this. All right. As I said, this is being. Okay, I'm going to evaluate it. As you can see, this is epidemiological workflow, right? I'm saying, okay, create certain model with susceptible, exposed, infected, and so forth. Tell me which is the symptomatic population, simulate for 240 days, and so forth, right? You can see some of this is being generated here, right? The code which is being produced. So this technology right now, I'm using it mostly for machine learning languages, but it can be applied to any kind of computational workflows for which you have enough idea how they can be staged. The next thing, I'm sorry, here Zoom is inviting me to do something else. It's an obstacle to browse. So that's why I'm slowing down a little bit. That's a very important slide. This was my third choice for talk. So my first choice was becoming the best Python programmer I know. It was rejected within 25 minutes by the Wolfram Technology 2022 committee. And by that, I mean Daniel Lichtblau. You can go talk to him about it. In all fairness, I sent him a 2-worded email, which is, I agree. And that presentation was also rejected by PyData Miami 2022. So, but you're going to see some elements of this. The reason I'm mentioning this is that originally in this project, my primary languages I targeted were R and Wolfram Language, the other way around. Wolfram Language first, R, right? But then probably 60% of everything you see is also covered in Python. And it's a nice overview of the functionalities, because some of these packages I have developed them in Mathematica and I have developed them in the last say 4 or 5 years in Python. Excuse me. I re-implemented everything within a month and a half. All right, so there's a book called with that name. There's a GitHub repository. I thought I'll finish the book before coming to this conference. It didn't happen. Okay, let me find my presentation. All right, so a few years ago, I started a book titled "How to Be a Data Scientist Imposter." Then turned out that I have to the know-how and the philosophy behind being a data scientist imposter, it needs to be separated from the actual know-how, how to do the computational pipelines. And you can see if you use natural language, it's much easier to explain how to be an imposter. So I started this simplified machine learning workflows. I always think that it takes me like a week to finish it, and there's always something else happening. a related book, which is really quite finished. It's software design methods in Wolfram Language. It's needed to explain monads. It's not needed if you use R and Python. In Python, I use object-oriented programming. In R, I use whatever kind of stuff we already use, similar to monads. So, all right. So classification workflows was the first monad, the first non-trivial monad I implemented. And I'm going to go into some more detail here. Not sure how well is this being seen. So imagine you're going to a competition for making a classifier, like say Netflix price. They give you say 500 movies with different ratings. They say, can you actually, predict who is, predict ratings and so forth, right? For the movies people haven't seen. So these judges, they have two sets. One is a training set and another is a testing set. They don't give you the testing set, they give you the training set. You take this training set and you can split it, or you split it into training and testing data. And you do this multiple times and you train classifiers and you see measurements and whatnot. And then at some point you might use all of the data to make a classifier and submit it to the judges. The judges don't let you submit very often. Actually, you can submit very often, but they don't tell you what is your score. They don't want you to kind of bombard them with, with tests and basically hyper-tune, train to the testing set they have. So the judges tell you, okay, you can submit once in 2 weeks or whatever, right? Or whatever it is, Now, basically, this is kind of fundamental workflow, which is kind of shown here in this diagram. Yeah, we take the data from somewhere, transform it, we compute some summary statistics, we train the classifier, we check accuracy and prediction. If we have too many classifier trainings and no good results, well, we might stop and so forth, right? So this workflow here is being implemented into this monad. This pipeline here basically goes through these steps here, allows you to do that. So when I say I have flowcharts for all of these subcultures in machine learning, this is what is happening here. I said this is the flowcharts, then I have the actual monads, and then I have additionally some natural language interpretation to this. So it's sometimes, we can see this code when it is generated. You see, like say, silicon classifier measurements. This because I'm using neural networks and this is just heuristics, they don't necessarily provide good results all the time. So when I evaluated this, right? Let me actually see. So when I evaluated this is so this is figuring out what this text was saying. It generated the code, and now I'm evaluating it here. It says, look, I don't know what are your measurements, data DS Titanic. So that's why we're using the default one. So they're like different kind of fail safes baked in both into the natural language interpreters and to the actual monads. So very often people tell me, well, I don't want to use your monads. Oh, okay, whatever, right? Then use the built-in, not built-in, but in this particular case, use the built-in language or use whatever other package or language you want to use. This is one of the things to kind of go. This is the imperative way of doing it with built-in commands of Wolfram language. It is not better or prettier or more easy to understand than this pipeline. All elements in this pipeline should be very clear. We start the monad, we split the data, we echo data summary, we make a random forest classifier, we show the measurements and the log plots. I don't think this is that obvious as here. And I didn't program it intentionally obscure. I'm just saying it's the case. All right, so most of the special features of this is what allows ensemble classifiers. This is not something built in Mathematica. I wrote some article a few years ago about this, 06, right? In which ensemble classifiers are discussed and how we can specify them. One of the things to consider is to also have receive operating characteristic functions, which is fairly important. I'm not going to go into details, but you can see here I'm specifying several logistics classifiers, you can see, well, unfortunately, several trainings are happening while I was doing this. Basically, all these free classifiers were trained, and then there's some kind of ensemble, ensemble classification was made. All right. So latent semantic analysis workflows, I'm not going to go through the rest in such detail, but I'm a big fan of dimension reduction, and this software Monotic includes quite a lot of dimension reduction methods: independent component analysis, non-negative matrix factorization, and singular value decomposition. All these functions, they also can be found in the Wolfram function repository, right? Singular value decomposition is built in. I'm talking about the other two. So similarly, we have extracted the workflows. We can see, like, again, we take the data, we filter it, massage it in some way, then we make the document term matrix, then we do some dimension reduction, then we do some other things. And so, so here you can see I have, I'm using some collection of text corpus of abstracts, and I'm extracting 20 topics. These abstracts, they're Mathematica, from Mathematica conferences, from Wolfram technology conferences. And you can see some of the topics here, they should make sense, like neural network framework, train, learn, whatever, right? Also, we can look at statistical thesauruses. And again, some of these statistical thesauruses derived these words here, they should seem to be synonyms. You can see I have stamped the words, right? So this gener is generating or generation, deployment, and so forth. All right. This is not just for text collections. I've published some articles about this in community. Here I'm using Python to compare Python and Mathematica and R. And with Python, I generate the same data set. But then at some point, I start using these monads to actually extract the topics. And you can see with singular value decomposition, we get one set of topics. With non-negative matrix factorization, we get another one. It's a very interesting comparison. In my opinion, explains much better and faster what is the idea behind this. Similarly, we can do it with digits. So this is an average 5 written by different people, and you can see how this increasingly becomes more. For some reason, I cannot zoom this. Increasingly become more detailed, right? And here with non-negative matrix factorization, we see different ways of writing 5s. Quantile regression is one of my favorite things to do. I'm surprised that people, after they see quantile regression, they don't drop anything else and start doing quantile regression instead of linear regression and whatnot. There's a guy, a professor. He was both a professor in statistics and economics in University of Illinois, Roger Kionka. He was a supervisor of the husband of Shadi Asnai. Shadi is the director of image and video processing department at Wolfram. So anyway, I talked to him, met him. He's doing stuff with R, right? Mostly, I'm basically doing quantile regression with R and Mathematica. Very similar type of, idea. We transform the data, we compute summaries, we delete missing values. We start doing the regression fittings, and then we do something else. Like you might detect anomalies. Last year, in 2019, I had a presentation titled "Detecting Anomalies and Structural Breaks." It was based heavily on quantile regression. All right, so you can see here quantile regression workflows. Let me see. Actually, I need to speed up, I guess. So you can see here, I'm doing quantile regression for 3 different quantiles at 10%, 3 different probabilities at 10%, 50%, and 70%. I'm also doing linear regression fit, and I'm also doing some linear regression with neural networks. And so it was taking too long to train that network, but you can see here, right? These are the results with the quantile regression. Mean corresponds to the linear regression, and net corresponds to the net. So what I'm saying is this workflow, it's not just for quantile regression. You can include other regressions if you want, right? And it can use different bases, like say B-splines and Chebyshev polynomials. We can draw an analogy between Quantile regression and neural networks. Both are using optimizers, right? So if I show you this, I can overtrain this. I mean, very often in neural networks, we try to overtrain the neural network in order to see the boundaries where things are and etc. So this is what is happening here. I can have different orders of training, you know, and so forth, right? Okay, I'm not going to expand on this. So, I mean, I've mentioned this several times. There are other programming languages to be targeted. So you can see, for example, here, latent semantic analysis is being also, Python is being a target, I is being a target. This is all, you know, being done. This monadic pipeline, it's not exactly monadic, but through the object orientation in Python, something similar is achieved. All right, so I'm not going to talk about recommenders much or at all. Let me make a decision. Anyway, recommenders are bread and butter for my, I mean, 60% of the time I'm doing recommenders. I'm using recommendation systems. I'm creating them very quickly because they're first level of regression. There are like 3 levels of regression. To study the data is the first level. The second one is to find the important variables. The third one, how to influence the results with which variables and what values. I do use recommenders to study data. So very often, not just for recommendations. So random data generation, the only reason I'm including this is that most of the time data scientists, they actually do data wrangling and, you know, and data acquisition, not some learned work like artificial intelligence and whatnot, right? And so here, if I exemplify what data science is doing, again, you can make some big pipelines of data transformations, but most of the time, you know, I personally, I'm in this realm. If I try to illustrate what is data science with trucks, I actually deal with quite a lot of strange data, right? The idea is how this can be streamlined in some way. One way to do it is this. I basically have some workflows which are for tabular data. And I have talked about this extensively, right? So first I made the conversational agents, the code, the translation monads for the standard machine learning workflows. But people didn't pay attention much, or the target audience, they were actually, it seemed to be much more triggered if I show them data wrangling. So this is what was happening. So you can see here this data wrangling stuff. Again, this diagram shows the summarizes the data wrangling status, and you can see that I'm translating English Bulgarian through some interpreter to different languages and packages in them. And as I mentioned earlier, if I can translate to a programming language, I should be able to translate to other natural languages. Very popular thing is when people see these systems like, oh, can you translate Python pandas to wherever else, right? I guess people get familiarized with Python pandas. They want to see how to do it in other languages. Python pandas is not, it's not a good design. I don't know why they do it, but I'll probably first do it with tidyverse and then with Mathematica. All right, so yeah, there's some, I have done this extensively. I need to wrap up here, but for example, somewhere here, you can see I have this notebooks in which all of these commands, like say, I think this is in, okay, this is in Wolfram Language. There's also one in Python, right, with pandas. So I have done Jupyter notebooks for R, Python, Raku, and Wolfram Language. And they do have this data wrangling capabilities. And since I have 1 minute left, I don't need to talk about workflow combinations. Yes, of course, all of the workflow combinations, all of the workflows we should be able to combine them. Definitely all the data wrangling workflows combined with anything else. The parallel construction is how I did it with Python. And these additional topics, well, in general, people want to do some vertical lock-in. And there is no reason for me to adhere to that. I'm actually saying, maybe you don't know the models or don't know the code or don't know the packages which do the machine learning, but you don't own it in a variety of ways, meaning you have some abstraction which allows you to surf through the different providers of machine learning. And this is a call for collaboration. And my future plans is to finish the book, make Padlets for all of these monads. And thank you for your attention. I don't know how much time we have for questions. Probably there is none.